So in number 23, we've got a cross-section of the Earth not shown to scale. And we realize that the Earth is actually not uniform in density. We've got the crust, the mantle, and the inner core. The masses and dimensions of each one of these is shown in there. Suppose that the Earth has a total mass of 5.98 times 10 to the 24th and a radius of 6,370 kilometers. Ignoring rotation and assuming the Earth is spherical, determine the acceleration of gravity at the surface. All right, that's pretty straightforward. We just have to use the acceleration of gravity as gm over r squared. In this case, plugging in the mass of the Earth, the radius of the Earth that they just gave us up on top here. This one's pretty easy to solve. We're just plugging in this, and we've got it. If we do that, you'll discover it should be about 9.83 meters per second squared. Give or take, a little bit larger than we expected. We expect 9.81, but awfully close. Next, B. Suppose a borehole, a mole hole, that's a hole driven down right here to this boundary, was drilled. What would be the acceleration of gravity at the bottom of this? Well, to solve this one, we have to actually figure out, all right, how much is the crust going to affect then the gravity at this point? Well, if you remember, being inside of a hollow shell, we would feel no gravitational attraction or force from this shell. So we can actually ignore this mass entirely. And so it's just going to be the mass of the core and the mantle that's going to affect the acceleration of gravity at the bottom of the hole. You can almost think about it almost like a corollary to Gauss's law. It's just the mass contained inside of this shell. In this case, if we do that, the mass, we have to subtract the mass of the crust. It turns out that is not a substantial amount. It's relatively small. And so it reduces the total mass now of the core and the mantle down to this. Our radius is also a little bit smaller. It's now this distance. I put it in scientific notations down at the bottom. And if you do it, interestingly enough, at the bottom of the hole, gravity is actually a little bit larger at the surface. And you might say, whoa, wait a second, what's going on? Well, it turns out the crust is a lower density than the rest of the Earth, whereas the core and the mantle are more dense. And so even though we went down a little bit, got closer, R got smaller, that helped a bit. The mass didn't go down all that much. And so gravity is actually a little bit larger as we go down. Now, C, suppose the Earth was a uniform sphere. Now, what would be the acceleration of gravity if you went down to the crust mantle boundary? Well, first of all, we got to figure out what the mass of the core and mantle would be. And to do that, we're doing that usual trick. We're figuring out what fraction of the volume these two pieces would have compared to the entire mass of the planet. And if we do that, we can just take the volume of this shaded region over the volume of the entire Earth and times the mass of the entire Earth to figure out proportionally what would be the mass here if it was uniform. Plugging it in, 4/3 pi r cubed over 4/3 pi r cubed times the mass. We'll discover that the mass of the core and mantle together, if it was uniform, would be 5.91 times 10 to the 24th. Notice that is less, slightly less than what we had here. If we plug that in, along with our radius now, we'll discover that, if the Earth was uniform in density, yes, acceleration of gravity would drop as we went down towards the mantle and the core. Hopefully this helps and makes some sense. Have a good night.